This lesson is a review on graphing with all three of the methods that we've learned about so far in this class. There's three different ways that we got a graph, and again, all three methods are just different ways to get to the correct answer. Any of them would work in any particular situation, but I want us to be familiar with all three methods because sometimes when you start a problem, it's easier to use method number one, as I'm calling it up here. And sometimes when you start a problem, it's easier to use method number two or method number three, but I want us to be familiar and comfortable using all three. You may have your favorite, one that's kind of your go-to or one that you feel more comfortable in executing than in some of the other ones, and that's all right. But just realize that any of them will work to get you to the correct answer. I just feel I want us to be able to know how to use each one because sometimes one's a little easier than the other. The first method, method number one, as I'm calling it up here, that we learned how to use was graphing using ordered pairs. Maybe some kind of equation set up like the one I have up here, y equals 4x minus 3. What we would do is we'd make an xy table, and we plug in 0, 1, and 2 for x to find three different ordered pairs, and once we've got those three ordered pairs, plot them on the grid, make a graph of the equation. So that was method number one we used to find our graph. Method number two is finding the x and y intercepts. In this method, I would still make a table, but what we often did instead is we put 0 on one side, 0 on the other side of the table, showing that I'm going to plug in 0 for x one time, see what I get for my y-intercept. Plug in 0 for y in this equation, see what I get for my x-intercept. Like for this particular example, if I put in 0 for x, again it would cross off the x term because when I put 0 in, essentially cancels that part out. 35 divided by 5 just gives me 7, so my y-intercept would have been the point 0, 7. Up on the y-axis, 7 spots. If I put in 0 for y, it would have canceled out this first term. 35 divided by negative 7 gives me negative 5, so I would go left 5 on the x-axis, and there would be my x-intercept. And using those 2 points, I can make the graph. So there was method number two that we learned. And now method number three, as we've just started working with in this class, using slope-intercept form. Again, why is this a nice form, or why is it called slope-intercept form? Is because I can find the slope and the y-intercept very easily in an equation if the equation's set up right in slope-intercept form. Slope-intercept form is just y equals mx plus b. Or, just like we see in the problem up above for method number one, I just need to have the equation solved for y all by itself on one side, and then I can pick out those two key important numbers. 3y equals 6x minus 12. This problem right here is not in slope-intercept form. But what I could do is I could divide every number by 3, every term by 3 in this problem, and get y equals 2x minus 4. Now it's in slope-intercept form, and just kind of continuing down here. Once I have an equation in slope-intercept form where it's y equals and everything else is on the other side, this number right here, the coefficient of x, this will be the slope of the equation, so my slope would be 2 for this case, and my y-intercept would be whatever the constant is out behind the end of the problem there, so negative 4. So my slope is 2, my y-intercept is negative 4, and just using that information, I could graph the equation. All three of these, again, all three of these methods we know how to graph with, but now we can just be able to use any of the three in any case, and I want us to be comfortable using any of the three, and just know that sometimes one is easier than the other. So I want us to be able to look at a problem, analyze it, and say, oh, this one I should use method number 2, or this one I should use method number 3, because it'll get me to the answer the fastest. For the other part of this lesson, I'm just going to go through a few example problems and just kind of show us that, for one, it wouldn't matter which method we use. We can get the same result, the same graph, no matter what method we pick. And also just the fact that, again, you can even change an equation around to get it ready for whatever method you'd like to execute for that problem. So any method will work for any problem. In math, very often, there's more than one way to get to the answer. And the same is here. The same can be said for graphing an equation. There's 3 different ways we can get to the right answer. Doesn't matter which one we do. I just want students to be able to look at a problem and analyze and say, oh, this one would be the easiest method for this particular problem. As I'm looking at this first problem here, y equals x plus 2. So if it says to graph that equation, I'm going to look at my 3 methods and think, well, which one would I probably use for this problem? Right away I can tell you there's probably 2 methods that I think it's set up well for, and I'm going to just use both those methods and show us again that the answer wouldn't matter whichever one we use. I'm going to look at method number 1 here, finding some ordered pairs. I think this equation is very set up well for that method. I could make some kind of table some XY table and plug in some numbers. Again, I usually just pick 0, 1, and 2 because those are easy to use. And if I put in 0, 1, and 2 in this equation, I'll get answers out pretty quick. 0 plus 2 gives me 2. 1 plus 2 gives me 3. 2 plus 2 gives me 4. So again, this equation, because it's y equals, and then my independent variable on the other side, it's easy to plug numbers in and get answers out pretty quickly. If I wanted, I could also use the third method here. It's set up well for slope-intercept form because this equation is in slope-intercept form. It's y equals, and then mx plus b, or my other terms are on the other side of the equation. So it's also set up for slope-intercept form. So I'm going to use that method right here. Looking at this equation, if there's no number, no coefficient on x, we do know that there is usually a 1 in front of that number. It's just implicit. We don't write it in. But so I could say that the slope of this equation is actually 1, and then my y-intercept would be 2 in this case. So I could pick out that key information and also make the graph. At this point, I'll probably stop and talk to the class too about, okay, I'm going to use 2 different methods to graph this equation. I'm going to graph both of them on this same grid right here. So what are my answers going to look like? Will the blue line and the green line, will they look different? Will they look the same? Will they look similar? Just different slant, different y-intercept? What will happen? And what often we can come to realize is, just like I talked about again in math, like I said earlier, there's different ways to get to the same answer. Both of these methods, whether I graph it with the blue, with the kind of what I've done here in the blue, or what I've done in the green, they're both going to give me the same answer. In both cases, I'm still just graphing this same equation, y equals x plus 2. So whether I do it with the blue stuff or the green stuff, again, in either of those methods, method 1 or method 3, I still should get the same exact result. If I plot these 3 ordered pairs like I have here in the blue, 0, 2, 1, 3, 2, 4, they're the 3 ordered pairs that I would get. I draw a line through those, and there's the graph of my equation using ordered pairs method. If I graph it using slope-intercept form, my y-intercept would be 2, so on the y-axis I would go up 2, put a point, and then again my slope of it's not in fraction form. I can change it into fraction form, and I can put this as 1 over 1, which reminds me that I have to go up 1 and to the right 1, so I have to rise. It's rise over run, so up 1 over 1, or up 1 to the right 1, as I should say, up 1 to the right 1. There are my 3 points, and again, just like I was talking about, both the lines are exactly the same if I had a nice ruler and could put them right on top of each other. So again, these 3 methods of graphing are just 3 different ways you can get to the same exact answer. All of them perfectly good. Just sometimes one is a little easier than the other. Again, just going to go through a few problems here and demonstrate that any method will work. For this particular problem, y equals negative 2 over 3x plus 2. This one, I think there is one method that's better than the other 2 if I'm going to graph this equation. I would say probably using slope-intercept form, the new one is probably the best, just because right here in the middle of the problem we have a fraction. So if that coefficient of x has a fraction on it, if I tried to use ordered pairs, method number 1, if I tried to use that method, when I start plugging numbers in, I might get decimal answers, and sometimes those are a little tougher to plot just because you have to plot like 2.6 or something a little different. So I could definitely use method number 1. It would work out just fine. But from this problem here with that fraction for the slope, I think it is a little easier to use slope-intercept form here. I can pick off m, I can pick off b, because my slope, I usually talk about it that ratio in terms of rise over run anyway. And then in this case, it will just be a fraction already, negative 2 over 3. That's already a fraction for me now. Now I just have to know that I have to go down 2 and to the right 3 to find more points on the line. So it kind of works out that it is a fraction for this problem. My y-intercept is 2. And so now if my y-intercept is 2 on the y-axis, I'm going to go up 2 spots and put a point. There's the y-intercept, whatever this line looks like. I know the line goes through that particular point, so it's kind of a nice starting spot for me. Again, if I'm using this method, sometimes I just like to recommend to cross off the y-intercept then, so we don't try to confuse it with the slope and get it mixed in with it. I use the y-intercept. Great, that was a good starting point. Now I go to that point and say, okay, it says to go down 2 and to the right 3. So down 2 to the right 3, there's another point. Down 2 to the right 3, there's another point. And I could keep going like that, but I really just need 2 points anyway. So there's the graph of my line. I missed that first point just a little bit, but you kind of get the idea. There's the graph of that equation. Again, method number 3, I think, would be the easiest method for that one. That's something I would like students to be able to kind of look at and see as we keep working on these graphing problems. Going on to another problem here. This one says 6x plus y equals -9. So again, here's another problem that I could graph using any of the three methods, but I think the easiest one for this problem is method number 2, the intercepts method. Why would I say that? It's usually, and as students will kind of start to figure out here at this point of the lesson and this point of the year, is that when they see x and y are on the same side of the equation, then that's probably the method to use, because then I can make my table, plug in 0 for x, 0 for y pretty quickly, and find the two intercepts. I will use this, or graph this problem using another method as well, just to show you again it wouldn't matter which method I use. But I think intercepts method is the easiest one for this problem to start off. So let's graph this using intercepts method. First thing I'm going to do is plug in 0 for x. That's what the first point says. So if I put in 0 for x, it gets rid of the x term. What's my y-intercept? Well, now it's just -9. Nothing leaving enough to solve in that problem. It just says y equals -9. Going back to the original equation, if I put 0 in for y, to solve that problem for x and get my x-intercept, I just got to divide -9 by 6. In this case, that'll give me a negative answer. I think -9 divided by 6 gives me -1.5. So I got my intercepts there, 0, -9, and -0.5 and 0. So if I plot those 2 points, 0, 9 on the y-axis, that means I go down 9, put a point right there, -1.5, 0. That means go about 1 and about a half, and then 0 on the x-axis. There are my two intercepts. There's the graph of my equation. Now again, though, I use method number 2, so that's fine. That obviously works for this problem. But if I want to do some other method, any of the other ones would work just fine too. I would have to switch around this equation, though, to use method 1 or 3, though, because it's not right now solved for y. So let's say we're going to use some other method, though. Let's say we're going to use using slope-intercept form. If I want to use method number 3, that's fine. I can definitely do that, but I got to get this equation arranged the correct way. I got to get it in slope-intercept form. How would I do that for this problem? Well, to get y by itself, I'd have to subtract 6x from both sides. That would eliminate it here on the left side. And so now all I got left is y equals, that's what I want on the left side, y equals. On the right side, I'd have -6x, and then we'll say -9. We'll just arrange it like that. Now the equation is in slope-intercept form. When the equation is in slope-intercept form, I can pick off the two key numbers, the slope and the y-intercept. The slope is that number right in front of x, the coefficient of x, that's -6. The y-intercept is -9. So there are my two important pieces of information. My y-intercept -9 means go down 9 on the y-axis. There's that point that we've used already before with the blue. And then the slope is -6. Again, as a reminder, if I want to write that as a fraction, that'd be like -6/1. I could think about this being going down farther 6, even though it's kind of going off my grid here. I could go down 6 into the right one, or just realize I can actually reverse both directions. I could go up 6 and left 1, just kind of keep myself on the grid here. So 1, 2, 3, 4, 5, 6, and over 1. So I can do that as well. Either way, as long as I end up with a negative slope. Remember, a slope that's going down to the right is a negative slope. As long as I end up with a negative slope, then I've done it correctly. I'll kind of reverse directions and do one more point as well. 1, 2, 3, 4, 5, 6, and over 1. And there's a point right there, and what do you know? Just like we were talking about, it doesn't matter which method I use, I get the exact same graph of that equation. So again, what I want students to start to realize is this kind of lesson we're doing right here is just kind of it's not exactly in the book, but something I want us to realize. In the book, we've dealt with all three of these methods for graphing, and I just want us to see that any method works just fine. But I want them to start to get used to the fact that they can look at a problem, analyze, and say, oh, this is the method I should use for this problem because it's the easiest. It wouldn't matter which one you use, but I want them to start being able to pick out the easiest method for each problem.